look out far enough, and why? Further and further down, so that d squared over 4 is negligible compared to y squared. This thing will simplify in a rather interesting way. First of all, what can we say about this? First of all, the signs are additive. The magnitude of the electric field, we add these two together, and maybe I could have done it over here. I just want to point out a couple little things. Okay, first of all, this is always valid. For any electric dipole or any separation of charges, this is always correct. All the other simplifications, the textbook talks about an electric dipole and the field due to a dipole, that's just simplifying the numbers and simplifying yet a new equation. But this is always valid. This is never not valid. So you forget an equation, you solve it this way. Never a problem. Okay? Now, however, this being said, you could have just as easily said, for this particular orientation, the electric field at P would be equal to the sum of this plus this in its particular direction. So I'm going to say it's minus 2q over 4 pi epsilon naught y squared. That's the magnitude. If y is significantly larger than d squared or than d over 2. In other words, you can neglect that small term because they're squared. 8 to 1 is different, 64, 65, pretty doggone close to 64, for instance. In the I direction, what we say was the sign. So it's d over 2. The way we can write the sign is to write it as d over 2y. That's another way of writing the sign of the angle. I think I'm leaving some d over 2 divided by y. This thing reduces to qd over 4 pi epsilon naught. There's something, I've got a y cubed. And this would be in the x, in the I direction with respect to this orientation, it would look like this.
I remember seeing that QD.
The moral of the story is basically this. In terms of distance of separation, if you look laterally to the orientation of the charges, and you get far enough away, the electric field decreases in magnitude as the cube root, or I'm sorry, as the cube of the separation distance, not just the square. So it's just, it tells you something because of their orientation, because it's only this component that has any value. It's not the full magnitude of the electric field, which goes as 1 over anything squared. I'm missing a 2 in here somewhere, Russ, and I'm trying to figure out where that 2 is. I cannot figure out where that 2 is.
Somehow it's in the numerator because it turns that 4.
Yeah, it turns it into a 2. And I know it turns it into a 2, and I'm not sure if it's this here that's causing the problem. I don't know, it's somewhere in here, and I'll figure it out at some point when I don't want to waste the class time to do it.
Are you just using that in that direction as the ratio between the two lengths of the triangle for d2 over y?
Repeat that.
For that factor of d over 2y, is that just the ratio of the lengths of the triangle?
Oh. Okay, there's a little dumbass moment. D over y is a tangent anyway, or this over that's a tangent. It wouldn't be this, right? Nice, I'm humble. it would look like, what would it look like? It would look like d over 2 divided by the square root of d squared over 2 plus, that would be the, would that be the sign?
Since it's opposite over
Y comes
hypotenuse.
out anyway, I guess it comes out just the same for some darn reason.
I was just trying to see where the 2 went.
I don't know where the 2 went. I'm staring at this thing, it's like having my pen behind my ear and wondering where the hell it went. I don't know, it's in there, I'll clarify it, I'll email it. 'Cause I know it's in here, and I'm looking at this thing, and I don't know why it's not immediately obvious. I'm sorry, I'm on tape too, that's it. It's in here, but the point is it diminishes as a cube. And it turns out that even if you look along the x-axis, it would also diminish as 1 over the cube of the x direction. And if you're anywhere else, I'm just not wanting to do every possible orientation, but it turns out that for an electric dipole in general, the electric field magnitude always diminishes as 1 over the cube of the separation. Because the positive and negative are always together, so they're always working against each other. The quantity QD, if you look from positive to negative, so I'm going to say, as we go from, negative to positive charges in direction, this is called the electric dipole moment. And it comes into play when we talk about it in other ways. I won't talk about it today. But as a matter of sort of rounding out our discussion, this quantity, Q times D, because it usually is the fixed quantity. Again, you've got some charge. And how does that charge affect space? The fixed relationship D between the two, the positive and negative charge, is what we would otherwise see, you might see it in chemistry as well. It's referred to as the electric dipole moment, or P. And the consequences of it have to do with torque when you put this in another electric field. We'll look at that one on Thursday anyway. So I'll figure out what I did with that 2, because I know that 2 should be either. This should be a 2, and it has to do with this.
Well, one thing I'm noticing is different right away
There's something in that.
between what they're doing and what you're doing, is you're using Y, which is orthogonal to the axis of the dipole, and they're using Z in the book, which is parallel to the axis of the dipole.
Oh, yeah, they're looking this way.
Right.
But it turns out it actually it diminishes in the, oh, you know what?
They just called you to do something else.
This is absolutely correct for this orientation. There's nothing wrong here. If you look on the x-axis. This is it. So we will readdress that and talk about the consequences of that. You look at something and you're expecting a value for some reason, you convince yourself it's wrong. In this case, it wasn't. I couldn't see it. What the heck I was doing? There, I know it is. No, it's not. It's not good.
I don't know how these ones dice with that.